We start with how the image logs can explain the stratigraphy. First of all, to understand that the image logs perform the borehole imaging, it need not be drill core. The borehole is there, camera is inserted, photo is made, 360-degree vision is made, and that can be explained as uncoiled image. And the principle of interpreting planes of various orientation, whatever I have discussed so far with the drill cores, remain the same with the image logs almost. Image logs are useful to study lithology, sedimentary texture, paleoflow direction, fractures and in situ stress. Here we are restricting into stratigraphic interpretation, that means how the layers are oriented, their concordant and discordant relations. Now, the high resolution image logs can give information on the sedimentary texture in millimeter scale. So, depends on the resolution of the image logs. We are going to use the word FMS, which is the abbreviation of the formation microscanner. Now, besides the planes being intersected on the drill core or on the borehole, a second aspect becomes important to study, that is the light shaded areas in the FMS image, which we are going to see with real examples soon. It indicates resistive, dense and cemented rocks, or it can indicate organic matter or hydrocarbon occurrence. And the dark areas within the FMS images, it indicates conductive clays, shale and water content in void or pore spaces. Water is conductive and therefore, that is reflected as the dark area. So, more and more conductive regions will be indicated by darker areas in the FMS images, and the less conductive places within the drill core or within the borehole is indicated by the light shaded areas. So, there are two sets of information that we are going to use in interpreting image logs. One is this what I said right now, and second what I have been stressing as lengthy lectures as the planes that intersect a drill core. So, these two sets of information we are going to use. We are going to demonstrate in terms of the sedimentary facies and stratigraphic interpretation. A question remains, what about the igneous and metamorphic rocks, their resistivities? How much resistivity difference will be reflected in what degree of darkness within the image? How far the resistivity difference can be reflected in terms of the color difference? Look at the physical properties of igneous and metamorphic rocks, find out the conductivity difference, try to see in research papers whether various igneous rocks can also be discriminated and the metamorphic rocks can also be discriminated in this way. And in the course of upcoming discussion, a few terms we are going to use. Speckle means a small spot or patch of color. A small spot or a patch of color will be indicated by speckle. Incise, this means mark or decorate with cuts. So, several cuts will be visible. We are going to see two kinds of images, static images. Practically it means uninterpreted image, and the dynamic image, it means that the image has been improved, maybe the color contrast has been increased and some curve fitting exercise has been done. We may not always see a clear cut sine curve like this, but things can be vague. So, here we can put a best fit curve we can set, and then we can go for interpretation. These are available in the dynamic image. Okay. So, here is a real image log being demonstrated. This one is the example of an uninterpreted image, or what we can call as the static image, and the right hand side one, this one is an example of the dynamic image. I have taken these examples and the sedimentary facies definition from the research paper by Lai and others from the Marine and Petroleum Geology journal. and here we are in particular demonstrating the circumferential borehole imaging log or the CBIL. In the static image, if we observe carefully, we can see certain lines such as this, and like that, and the line does not appear to be continuous. As I have demonstrated in terms of my simple diagrams such as this one. Here I said that the line may not be continuous and there can be some discontinuity. The curve fitting has been done, these lines have been made as a best fit. So, based on these lines, interpretations can be made. We can see in the image certain dark regions and certain brighter regions. This image is after improvement done based on this static image. We can see basically 3 shades of colors here. This is brown, this is yellow, and then there is white region, and after improvement there are certain black regions, brown and yellow, and the white region. And just to recollect, the dark areas indicate conductive materials and the light shaded region indicates resistive dense cemented materials. So, with this information we are now moving into the sedimentary facies definition. We start with the massive image facies shown over here. This is the static image and this is the dynamic image. We are observing different shades of colors, and what is the summary is written over here. The massive facies means that the sedimentary rock is massive, which means it has no structure, or it is structureless, which means it has no internal structures, which means obviously that there are no laminations, lack of grain size difference. Here we can see in the image we do not see lines, we do not see sine curves, and if we compare this massive image facies with the laminated image facies, which I am going to describe soon, or the cross stratified images, we can see lines and the sine curves, etc., which is missing over here. Since no planes are developed, therefore no lines curved or straight have developed. This massive facies can be divided into 2 types: the dark massive facies. Here the darkness will indicate mudstones or shells, and if it is a bright massive facies, then it will indicate sandstone, clean carbonates without any structure, or gypsum. What about the coal layer? I am putting this question for the students. Look at the image logs from the coal layer or speculate what is expected, and then link with the literature. The same color within the massive image facies, say it is all yellow, or here it is in this region particularly it is all brown, it indicates that there is no grading. Now here we cannot fit any sine curve, and that is what I am writing, poor fitting with the sine curve. If we summarize this in a tabulated format, then from the same research paper Lai et al., that is how it is summarized. The massive facies appearance is homogeneous or massive, structureless, dark massive or bright massive, 2 types, and the ability to fit a sine curve is very poor. The interpretation is what I have already stated. Now we will move into the next one, that is the laminated image facies. Lamination means millimeter thin planes developed within the sedimentary rock. So, you can see here the gently curved pattern, and these lines are very close spaced, revealed both in static as well as in the dynamic image. And what kind of rocks can show such lamination? The answer is shale abundant in organic matter can be laminated. So, based on laminated image facies, if we observe like this, we may be able to comment rock type, but we have to do that with great caution. We now look into the cross stratified image facies, and here what is the difference between the laminated image facies and the cross stratified image facies? First of all, the static image is dark, so it needed interpretation, so it needed improvements. In the dynamic image, we are finding the curviplanar lines, and note that these curviplanar lines, the white bands particularly, they are thicker, whereas in the laminated image facies they are much thinner. This is one difference. Now, we know from our sedimentological knowledge, if within sandstone the cross stratification has developed, it indicates a high energy environment. So, if we get such a facies and we have some idea we are dealing with sandstone, the rock type, then we can say that we are dealing also with high energy environment. So, in this way one after another arguments can be made and interpretations can be done. We are now getting into the speckled image facies. We can clearly see its appearance is quite different from the massive image facies. Here the appearance is mottled, there are irregular distribution of colors, bright resistive conglomerates can be one example and dark conductive muds and vugs can be another example. But just looking at the bright and the dark colors, we cannot guarantee the rock type. So, these things are just a possibility. Naturally, in case of speckled image facies, since there is no plane developed, we do not see straight line or curved lines or the sine curves. So, we can compare the speckled image facies with the massive image facies. Both are devoid of planes, but their appearances are different. Laminated image facies and speckled image facies, their appearances are different. Here lines are developed, here we do not have lines. Cross stratified image facies and the speckled image facies, they are different in appearance. We can give the real examples of speckled image facies. Consider mudstone clast rich in sandstone. So, here it shows a speckled image of conductive mud clast floating within resistive sandstone matrix. Or take the example of cavities and vugs in carbonates, they also appear as dark spots. So, where this spotted appearance will come? It will come when there are two kinds of resistivities found within the same rock type. Clast matrix supported sedimentary rock can be one example, but the resistivity contrast between them has to be severe. The mudstone clast rich sandstone will show such appearance, but what if the sandstone is layered, then will we get some sine curves inside, remains a question. Let us look at the convoluted image facies. This is coming from the convoluted layers, and if it is being drilled, and then we are looking at the uncoiled image. Now, these convoluted facies can be found in sand to sill size siliciclastic sediments. So, if we can comment that there is a convoluted image facies and we have some idea about the lithology, then stories can match. And what happens here? Since the layer is folded, the deep of the layers are changing, they can be haphazard at few places, they are non-systematic, and therefore, there are lines which are manifested in the static and dynamic image, but as you see they poorly fit with the sine curve. In fact, there are some elliptical appearances coming. So, my question to the students is what this can indicate, and can you simulate a structure which in the uninterpreted image appears in this way. Now, let us take the alternated band image facies. Here we are dealing with thick, how much is the thickness? More than 10 centimeter of alternate horizontal bright orange and dark brown bands, which can be checked over here in the static and the dynamic images. And in what way to distinguish it from the laminated image facies? We see here the bands are thinner, whereas they are thicker here. That is what is stated, much thicker than the laminated facies is being done. Now, in certain terrain you may not find perfect laminated image facies in this way, or the perfect alternated band image facies with this much of thickness. Lai et al. Has found it from certain terrain, and it may not be possible to apply as it is in another place. So, in your place you may find some in between facies, or you may define a new facies. It remains an open. While this remains our guideline, this is not the entire scenario of the geological complexity. Now, we are going to see the truncated image facies. Let us look at the appearance. We are finding sharp truncation here in the static image, and also over here there is extremely bright region in the dynamic image, then there are dark regions, and then there are bands clearly visible. This is clearly different from the speckled image facies, from the massive image facies, from the laminated image facies. The difference is clear cut. This kind of truncation is very prominent. Layers are there, and that is common with the laminated image facies and the cross stratified image facies. So, with this idea we now come into the description. The truncated facies are the truncations of underlying laminae or rapid change from dark brown to yellow color. We can see here rapid change from the dark brown to yellow color here to here is happening, and it is produced by truncation of the underlying laminae. Here we are calling as laminae basically layers, but we can see they are much thicker than the laminated image facies. So, instead of laminae we can call them layers, and there is a sharp truncation. And since this color contrast is too much, this light and then there is a dark band, there is too much of resistivity contrast between the sediments over here and over there. Now, these are commonly interpreted, these truncations are commonly interpreted as the scour surfaces or the reactivation surfaces cutting out of underlying sediments. On these scour surfaces, coarse grained sediments can lie, and below can lie the fine grained sediments. So, if this is a scour surface, then over here we can have coarse grained sediments, and here we can have fine grained sediments. The fine grained sediments preferentially moved up locally, and then over that deposition of the coarse grained sediments happened. We can also have a reactivation surface. Reactivation surfaces are produced by short term changes in flow conditions that modifies the shape of the bed form. Okay, now we are going to see the grading image facies. As the word grading is there, it can indicate two possibilities, either fining upward or coarsening upward succession, and in fact it can also indicate a Boma sequence. But do not link all the time with the Boma sequence. Look whether you are dealing with the marine sediment or the non-marine sediments. Now, what happens in a graded facies? There is gradual upward color changing from bright yellow to dark brown. This change is gradual. Let us try to understand. Here, if we observe these colors, we do not see a very sharp contrast between the different layers. We see a sharp contrast here in the alternated band image facies. We can see such contrast in the laminated image facies, and in case of speckled image facies we do not see at all, because there are first of all no layers. In convoluted image facies also we are getting sharp layers, but here we can see that the layers are not very sharply changing from one into another, which is also reflected a bit within the dynamic image. And now we are going to see the last one, the incised image facies. Here what we are observing, that there are layers given by the color contrast, and then that is cut by a bit thicker lines. What are these lines? These are the fractures or the structural planes that have cut across the units. From the static image we can see the dynamic image where the color contrast is increased, and these brittle planes are more clearly exposed. They look a bit haphazard. So, here is the incised facies. It is continuous dark and bright sine curves which cut off the bedding planes. So, here it is continuous dark and bright sine curves, and then there are dips deeper than the structural dip or cross bedding. Here is an exercise for the students how the image logs will look like if you are dealing with igneous and metamorphic rocks, and comment on the specific rock types, and for this hint look at the rocks properties for your comments, and then cross check with the literature. We are going to learn the geological time scale, which is an integral part of geoscience education and especially in stratigraphic studies. Since the birth of Earth, since 4.6 billion years till today, the geological time has been divided into several periods, which is the fundamental unit in geological time scale. It is just like using the term period in history, which you have studied in school. If we say the Gupta period in India, that means it is a certain time span when the Gupta kingdom existed. We will be using the term million years in the geological time scale, which is represented by MA. The other way is to represent by MY and also by MYA. There is subtle difference in these terms. However, practically we use three of them in a similar way. Once we say millions of years back from present, here present means what? Present means 1950. This is taken as the standard. And in geological time scale, we will be using geochronology, the absolute ages, and we will divide the geological time 4.6 billion year till today. We are going to I am going to demonstrate. Whereas remember, the term chronostratigraphy refers to materials in stratigraphic units, which effectively means rocks to be specific. I repeat, geochronology will deal with the geological time done by dating processes, and in subsequent lectures we will see what are they and how that is performed, whereas chronostratigraphy essentially means the rock column to be specific. Now, let us look at the different geochronological units, and they are eon, era, periods, epochs and ages. And as I told you already, period is the most fundamental unit. But note that period is in the middle. So, it is not the largest time unit, neither is the smallest time unit. The largest unit is eon and the smallest one is age. Now, in terms of chronostratigraphy, there are equivalent terms. Period is equivalent to systems, epoch is equivalent to series, and ages are equivalent to stages. Before moving into the geological time scale, also note that giga means 10 to the power 9, mega means 10 to the power 6, kilo means 10 cube, unity means 10 to the power 0 or 1, milli means 10 to the power minus 3, micro means 10 to the power minus 6, and nano means 10 to the power minus 9, and these are the different symbols to represent them. We need to remember certainly few of them in the stratigraphic studies. Now, as you see in this table, eon is the longest period of time within the earth history, and there are 3 eons. What are they? Archean, since the birth of the earth up to 2.5 billion year, Proterozoic 2.5 billion year up to 542 million year, and Phanerozoic 542 million year up to the present. Again, what is the meaning of up to the present? What is the meaning of the word present here? Here it means 1950. Now, if I demonstrate the geological time scale in terms of the international chronostratigraphic chart, here this is how it looks like. Eon can be seen over here. And as I said, the different eons are Archean, Proterozoic and then Phanerozoic. Here in these portions of the chronostratigraphic chart, you find that eon is the leftmost column, whereas not in this case. There is another column here and a term that is used, that is Precambrian. We will see why it is said so. Now, as per the latest stratigraphic chart, there is another eon that is known as Hadean, and Hadean eon varies from 4567 million year up to 4031 plus minus 3 million year. So, what is given in many of the stratigraphy books, this is not very perfect. We may correct it that there are 4 eons, and here we will write down Hadean is the bottommost or the oldest, and what is the time range? 4567 up to 4031 plus minus 3, 4031 plus minus 3 million years. Then Archean, this definition needs to be changed. it will be 4031 plus minus 3 million year up to 2.5 billion year. Now, eon is divided into several eras. As I am writing here, this is the time division of eon, and just for example, Phanerozoic, that means this one, this time is divided into Paleozoic era, Mesozoic era and the Cenozoic era. Let us see in the International Chronostratigraphic Chart. The Phanerozoic eon is divided into Paleozoic era, you see the term here, then which continues over there, then the Mesozoic era, the term is here, and then comes the Mesozoic continues here, and then here is the Cenozoic era. And not just the Phanerozoic is divided, there are also divisions of the Archean eon into Eoarchean era, Paleoarchean era, Mesoarchean era and the Neoarchean era. Note that Hadean is not divided into several eras, and the Proterozoic era is divided into Paleoproterozoic, Mesoproterozoic and Neoproterozoic. At each, all these numbers indicate the million year time divisions. These are all in the million year as stated over here. These are the numerical ages which is over there and over there. Now, I come to period, and I already told this is the most fundamental unit in the geological time scale, and I am writing here it is a basic unit of geological time. It is a division of era. These eras are divided into several periods. For example, the Mesozoic era is divided into from bottom to top or from oldest to youngest, Triassic period, Jurassic period and the Cretaceous period. Looking at the word Jurassic, you have rightly pointed out this is the time when the dinosaurs were maximum in number on the earth's surface. Let us look at the different periods in the geological time scale. The Hadean is not divided into any time periods. Archean is also not divided into several periods. The Eoarchean is not divided into any periods, Paleoarchean, Mesoarchean and the Neoarchean. Their division has not been made. But once you look at the Paleoproterozoic, Mesoproterozoic and Neoproterozoic, several names will be found, and these are all the different periods. Now, the geology students need not remember each and every name which is being shown over here. For example, a structural geologist needs to have only a basic idea about the geological time scale, and if a paleontologist is, for example, working very specifically on these ages or stages of rocks, then he might be interested in getting into the detail. I can tell you what are the essential names and the dates, millions of years and billions of years, that you have to remember. Okay. Now, we can divide Paleozoic into several periods. For example, Cambrian. Now, before Cambrian, whatever is there we will call as the Precambrian, and that is why it was written here. And you can see Precambrian is not a formal name coming within eon, era or period. Please be careful that Precambrian is not a formal stratigraphic name in that sense. However, the term is frequently used in stratigraphy. So, rocks younger than Cambrian is and is a portion of Paleozoic. Then comes Silurian, Devonian, Carboniferous, Permian, and when we divide the Mesozoic into several periods, the bottommost or the oldest one is the Triassic, then comes Jurassic, and then comes the Cretaceous. Similarly, if we divide Cenozoic era into several periods, the bottommost is the Paleogene, then comes the younger one Neogene, and then comes the Quaternary. These are the different periods. So, I can call Paleogene as Paleogene period. I should not call Paleogene as Paleogene eon if I say it is a mistake. Similarly, Phanerozoic, either you use the word like that or you say Phanerozoic eon, but you cannot say Phanerozoic era, neither can you say that it is a Phanerozoic period. The equivalent term of period in chronostratigraphy is called system. Now, these comparisons were already made over here. Systems are equivalent to periods. So, if the rocks, actual rocks deposited during the Jurassic period, we call the rock coming within the Jurassic system, that when we are referring actual rocks, then we have to use the chronostratigraphic units. So, therefore, Jurassic system, the word system has come over here to represent the Jurassic actual rocks. Okay. Now, the periods can be divided into several epochs. Early and late Cretaceous are the epochs of the Cretaceous period. Let us see. Here is the Cretaceous period. As per the 2024 December version of the International Chronostratigraphic Chart, Cretaceous is divided into Lower Cretaceous and the Upper Cretaceous. So, Lower Cretaceous is an epoch and a part of Cretaceous period. Upper Cretaceous is an epoch and is a part of the Cretaceous period. Now, you see that lower and upper has been made over here, but not at all the places periods are divided into lower and upper. For example, Paleogene period is divided into Paleocene, Eocene and Oligocene epoch. Here we do not say lower and upper. So, the way of classification language wise, term wise is non-uniform, and not just lower and upper, not just the different names. Sometimes we divide a period into three portions: lower, middle and upper. And do you note that the time duration of upper is much more than that of middle, and the middle epoch time is much more than the lower. So, one interesting thing in the geological time scale is that time has been divided non-uniformly.